The Leibniz series is an infinite series. But did you know that when you evaluate 5,000 terms, you actually get more digits right than when you evaluate 6,000? And when you evaluate 500,000 terms, you get more digits right than when you evaluate 600,000?
Yeah, sorry, that intro is a bit much, but it's a math story and it needed an intro. Let me first recall that there are many algorithms to compute pi, many very efficient algorithms. I mean, we know millions and millions of places of pi, so we do know how to compute pi. But there are also some very elegant formulas, and for this video we'll use these elegant formulas. Maybe the first formula that comes to mind is this one. Pi squared divided by 6 is the same as the sum of all the inverses of the squares. You could use this formula to compute the decimal places of pi. Now, if you do this, it turns out that this is actually a horribly bad strategy to compute pi. Actually, maybe let's simply do this. Let's have a look. So I have a little program here. You see it here. So I'm just summing from n to some value that I've called range, which is 100 at the moment. And then I'm just adding. So I have this variable value in which I'll store the partial sums. So I start with the value 0, and then I'm just adding the inverses of squares. These are the inverses of the squares. I sum them. So this is what's happening here. Then I multiply the result by 6 and take the square root. You might be wondering what the rest of the program is for, but you'll see that in a sec. So let's just run this program. Now here you see the added functionality. So what's special about this program is that it marks all the digits which are correct in a yellow little box. All the yellow little boxes, this means that these digits are correct. And everything which is not yellow is these digits are wrong. Back here you see how many terms have been evaluated. Yeah, so 10 terms evaluated means that I've just taken the first 10 terms of this sum here. You see right away how bad this formula is, because we're getting the first digit right, and then we already need round about 30 terms to get the second digit right. Let me first point out, why are there so many of these yellow boxes back here? Well, these are accidentally correct, because every digit that goes from 0 to 9, whatever digit you have, there is a 10% chance that it might be the right digit. And this happens occasionally, and this is exactly what you see back here. So all these yellow dots, this just means digits which accidentally agree with the correct decimal digit of pi, but you know, that's noise. There's no deep reason behind this. Let's try to get another digit right. We have the first two digits of pi right. Let me just increase the number of terms we're adding. So we could be going up to 1000. Let's have a look. So that means 10 times the computational effort, 10 times the number of terms we add. And you see, okay, we're actually gaining one digit here. We should go a lot higher. So let's take 100 times the effort we did so far. Yeah, you see, so basically now we have 5 digits right, but that's just at the cost that we have to evaluate 100,000 terms. So you see, in order to actually compute pi, this is pretty useless. This is not exactly what I wanted to show you. I wanted to show you a different formula where something more interesting happens. That's the formula due to Leibniz. And it goes as follows. It says pi divided by 4 is the same as the alternating sum over all the inverses of the odd integers. And this is the same as 1 minus a third plus a fifth minus 1/7 and so on. So we can use the same program to evaluate this formula. So this is the little program here. I've already modified it. So you see everything's the same. Again, we have some variable called value in which I store the value. And then you see here 4 times adding the alternating sum of exactly these terms which I wrote down. Good. And now let's evaluate the first 100 terms. You see that it looks very similar. With the 100 terms, we only get the first 2 digits right. And then we have some accidental noise of some digits which are accidentally correct. The story starts getting interesting when we evaluate more terms. So let me directly maybe jump to multiples of 1000 terms. So, and now something really curious happens, because look, for example, at the evaluation of 5000 terms, and you see long stretches of correct digits. Right here you have a long stretch of correct digits. Here you have a long stretch of correct digits. So the evaluation of 5000 terms is already pretty good. It gets a lot of the digits of pi right, but not all. Weirdly, exactly the 5th digit is incorrect, and then here are another 2 digits which are incorrect. and so forth. But this is not convergence. You might think, okay, so this is a sum, it converges, so the more terms I add, the closer I should get to pi. Yeah, true. This is exactly what happens right here in the beginning. But this is definitely not what happens here, because if you take the metric distance between this value and the limit pi, then this is not so good, because this little wrong digit 3, it destroys it all, right? I mean, the digit back here, that they are correct, it doesn't bring the number closer to pi. And then also note that as we sum more terms, so we evaluate 1000 terms more, all these digits which already were correct are now incorrect. So it's like all these digits, they were already very close to where they should be, but then as you add more terms, they get wrong again. So this is in a way different than convergence. It's more like if you were to compare the decimal expansions just by counting how many digits are correct, then this is amazing, right? This evaluation at 5000 terms is amazing. So many correct digits. But as I said, the actual distance between this value and pi is not much better than the distance of the number before or after, just because this one little wrong digit destroys it all. But so here it's super interesting, because why does this pattern arise? Why does this term, after this partial evaluation of this sum, get so many more digits correct than we would expect? And this is not just at 5000 terms, right? I mean, you also here at 1000 terms, you see a long stretch of correct digits. At 2000 terms, down here the same. And this pattern, it keeps happening as you go to higher numbers. So let's go to the millions. So now the evaluation takes a bit longer, but you see the same pattern happening, right? I mean, so here at 100,000 terms, there is one wrong digit, but there are long stretches of digits already entirely correct. And also here at 500,000, it's amazing, right? So here is one wrong digit, but then long stretches of entirely correct digits. And note, this looks really completely different from the pattern we saw with the other formula, right? Here we had all these accidental yellow little dots, which were true for no good reason. That just accidentally the digit matches. But here, this is definitely not an accident. There clearly is a pattern. Yeah, and this is what this story is about. I want to tell you why this happens, because this is completely understood. This phenomenon was observed by various people, but the explanation was found by the Borwein brothers and Dilcher. It's a really beautiful story, and it's definitely worth telling. So I will tell you exactly what they found out and how they could explain this phenomenon. So how can one possibly understand such an effect? The key strategy will be to rewrite this sum in a different fashion. You know, you can manipulate this so that the limit doesn't change. And we will try to achieve that there is a term where we divide by powers of 10. Because if you have any number and you divide it by 10 to the n, then what this means for the decimal expansion is that all the decimal digits are moved by n steps to the right. So if you are able to rewrite this in such a fashion that there is a power of 10 in the formula, this gives you a reasonably good control over where certain decimal digits occur. But it's quite difficult to get there, because you need to find a manipulation for this term so that these powers of 10 occur. A priori, it's completely unclear how this should work. And what we'll do is we'll first use a formula which is called Boole summation, and it's a general strategy to rewrite a sum. You know, you could say we're just lucky, because then when we do this, we'll see that the expression we get already has a much nicer structure for our investigation. So I should explain Boole summation to you. In case you know the Euler-Maclaurin formula, this will be fairly familiar, but I'll make this self-contained. So I'll explain this to you from the beginning. There is a big issue about convergence questions, as there is so often in maths. And at least at the beginning, I'll gloss over this a bit, just because this makes it easier to focus on the key story. So the first thing we'll need to know is the whole theory about Euler numbers. And by Euler numbers, I don't mean E, 2.718 and so on. I mean another sequence of numbers which are called the Euler numbers. They were invented by the same guy, Euler. It's nonetheless a completely unrelated story. All of this starts with the function 2 divided by e to the x plus e to the minus x. You might recognize this. This is actually the same as 1 divided by the hyperbolic cosine of x. But this, at least for this story that I will be telling you now, doesn't really matter. So if you don't know this, no problem. we start with this expression and we have the idea, okay, maybe we could write this as a power series expansion around 0. And this works. This function in the denominator is clearly analytic. It's an entire function. And if you plug in 0, you just get 2 in the denominator. And you know, if you invert an analytic function and its value is not 0, then at least in some neighborhood of the point where it's non-zero, the function remains analytic. So certainly it will be possible to expand this as a power series. And this is what we'll do. Of course, I have no idea what the coefficients in this expansion are. Let's just call them capital En. X to the n divided by n factorial. Of course, I could just not write this and just store the coefficients in here, but you know, I might just normalize my coefficients slightly differently and write division by n factorial here. Okay, so I have no idea what these numbers are at the moment, but I know that they exist. This will be some power series with some positive radius of convergence. And these are the Euler numbers. And very soon we'll know a lot more about them. To see why this is maybe interesting, it's good to rewrite this a little bit. So the first thing I could try to do is I could try to get rid of the e to the minus x here. And I can do this by just extending the fraction by e to the x. This gives me 2 times e to the x divided by e to x plus 1 now. And this is still the same. Oh, wait, actually, I can also simplify the right side because this is an even function. If I replace x by minus x, this just stays perfectly the same. And if you have an even function, then the power series expansion has no odd terms. So actually only even terms occur. So let me just write it like this. E to n x to the 2n divided by 2n factorial. And we've already proven our first little theorem about the Euler numbers. We won't really need this, but I'll, just for the record. So if n is odd, we've just deduced that the nth Euler number is 0. Okay. I'm sorry that this is a bit unmotivated at the moment, but you'll see soon why this is useful. So what I'll do is I'll replace x by a new variable, which is just t divided by 2. Let me just plug this in. So I get 2 times e t divided by 2 divided by e to the t plus 1 equals this sum. And now this changes also a little bit. Now I get t to the 2n divided by 2 to the 2n divided multiplied with 2n factorial. And this 2 to the 2n, this is just the 2 which I get from plugging it in here. This term here, it reminds me a little bit of a geometric series, right? I have to rewrite it a little bit. Let me show you how I can do this. I can do this in a fancy way in a different color. So I could rewrite this denominator as 1 divided by 1 minus e to the t. So minus is plus, so this is exactly the same denominator as here. But this is a geometric series. So this is the sum from 0 to infinity of minus 1 to the n e n t. Okay, I'll just plug this in. So I'll just copy first the numerator. So I get 2e to the t divided by 2. And now the denominator I write in terms of this formula. So times the sum from 0 to infinity minus 1 to the n e n t, and this equals the other side. I'll copy it even though I'm not planning to do any modifications on the right hand side. Okay, I can rewrite this even more, right? Let me just put this in here. So I get the sum from 0 to infinity, 2 times this sum, minus 1 to the n e to the n plus 1/2 t equals this expression. Okay, and now comes a step which is a bit bold. What I'll do is I will plug in for t something which is not a number. I'll just plug in a differential operator. This step is a bit bold. I'll explain it in a sec. Maybe in case you haven't seen this, let me just first tell you a little side story about what would it mean if I write e to the b d with d being the differential operator. So meaning the operator which takes the derivative of a function with respect to its variable. So what would it mean if I apply this expression, let's say f is maybe a polynomial. Now, the meaning of this at first sight mysterious expression is that I will just formally plug in d, this differential operation, into the power series which defines the exponential function. Let's just figure out what this gives us. So this is now a sum from 0 to infinity, and I'll now just plug it in the exponential series. So I get bd to the n divided by n factorial, the usual power series of the exponential function, and then I write f. Okay, but now I can rewrite this as the sum from 0 to infinity of b to the n divided by n factorial d to the n f. You might be worried a little bit why this is true, because so far I've all the time worked with numbers or functions, so everything commutes when you multiply. Of course, if you suddenly start plugging in a differential operator, you can't be so sure anymore whether stuff always commutes. But, no matter how worried you are, this will be fine, because if b is a constant, or I should have said this, so let's make b a constant, some complex number or a real number. So if b is a constant, then certainly if you first differentiate a function and then multiply with a constant, or you do it the other way around, it doesn't matter, because differentiation is a linear operation. So even though in general stuff might not commute anymore, using differential operators, these will commute. So I can collect all the terms belonging to the scalar to the left and all the powers of the differential operator to the right. So I get this expression. And now what is dnf? Well, d stands for differentiation, so this should be the nth derivative of the function. So I would say, if I allow myself to plug in a value into this function, maybe z, or z, depending on what your preferred type of English is, then I would expect that I get the sum from 0 to infinity, b to the n divided by n factorial, and then the nth derivative of f with z plugged in. And now you recognize, wait, this is exactly Taylor's formula, right? So this is Taylor. What this expression means is this is just the expansion of the function f around the point z, and I move b steps away from it. So this is the same as f of z plus b. If you want to evaluate this, and Taylor's theorem applies to the function f, you just would get exactly this expression. Taylor's formula, it has all the derivatives of the function at the point where you expand, and then exactly this expression. So, if you assume that f is a polynomial, this is all entirely rigorous. If you assume that f is not a polynomial, then in general there could be problems. So certainly we need infinitely many derivatives, so the function f definitely has to be smooth, but there are more problems, because you remember from calculus that even a smooth function, it doesn't have to be true that the remainder term in the Taylor expansion goes to 0 if you take more and more terms. So there's also a question here whether this converges and whether it really converges to this. So really you need more assumptions on f than just smoothness. Because I'm trying to explain an idea here, let's gloss over this a little bit. At any rate, for polynomials, this is definitely harmless, because after, if your polynomial has degree n, once you are in the nth derivative and you take a further derivative, it's going to be 0. So convergence is not an issue. And then also it's clear that the remainder term goes to 0. So for polynomials, this is absolutely harmless. And you see what a useful operation this is, right? It's a very elegant way to rewrite shifting the function. If you want to shift a function by b, you can rewrite this by multiplying with this operator. There is a more fancy interpretation which says that you're generally on the real line, you have the a Lie group action coming from shifting, and then this is the corresponding infinitesimal generator of this transformation in the Lie algebra. Well, we don't need that, but that would be the fancy interpretation. Okay, good. We only need this formula. And now that we've seen how useful it is to plug in differential operators in power series, let's apply this to the formula that we've actually been discussing, namely this one, right? This was the formula we're discussing. And I'll do the same. So I will now plug in the differential operator, the same one, for t. And then as before, this will only make sense if I apply it to a function. It's not really completely true, because even if you don't apply it to a function, you can still consider this as an identity of differential operators. But yeah, so good. Yeah, so what do I get? So we pick a function, and so if you want to be sure that stuff is fine, make this function a polynomial, but remember, a smooth function with additional conditions should be good enough. Good, and now, so what do I get here? So I get 2 times the sum from 0 to infinity, then this alternating sign term, and now I recognize precisely the expression that I've shown you here. If you have this exponential and you plug in a differential operator for t, then this term here corresponds precisely to shifting. This was shifting by b. So This term here, if I plug in d for t, will be exactly shifting the function by n plus 1/2. So that's interesting. So I get the function at z when I plug in a value, but shifted by n plus 1/2. Okay, and now the right-hand side. Well, this is, just the same. E to n, well, 1 divided by 2 to the 2n factorial, and then the 2nth derivative of z. Because, we plugged in d for t, and this was t to the 2n, so this becomes this. And this is the key formula for our investigation. So this goes by the name of Boole summation. So in the way that I've shown this to you, you need to be a little bit careful. F should be a polynomial, and we haven't really worried much about convergence, but roughly we now have a good idea that this formula might hold. And what's interesting about this is that we're considering a function on the left-hand side at various values, and we have such an alternating term. And now the idea will be that we'll try to bring the left-hand side of this formula into the shape of the expression in Leibniz formula for pi divided by 4. And then maybe this is helpful if we compare it to the right-hand side in some fruitful fashion. So that's the strategy. The function which we take for this is just 1 divided by x. So at this point you already note that something is delicate here, because Boole summation is only really harmless if f is a polynomial, and 1 divided by x is not a polynomial. So no worries, we will be staying clear of the point x equals 0. We're talking about a smooth function, but in principle it's a little bit delicate to see whether this converges. It's a real genuine problem, but let's gloss over this for the moment. So let's first see why this is cool anyway. So let's take this function. The whole idea behind taking this function is that we want to make this thing look like the term in the Leibniz sum. Recall, that was the alternating sum over the odd inverses of odd integers. So let me just unravel what you get. So what's the left-hand side? So you get 2 times this sum from 0 to infinity, minus 1 to the n, and now 1 divided by z plus n plus 1/2. So this is not yet really what we want, but imagine I multiply this with the denominator by 2, right? Then you get 2z plus 2n plus 1. So if z is 0, then you already get like 2n plus 1, which is the alternating sum, which would occur in the Leibniz formula. So that looks promising. Now let me also write down what the other side of the equation is. So this is the sum from 0 to infinity of the Euler number e to n divided by 2 to the 2n factorial times, okay. And now I need to know what the 2nth derivative of this function is. But this is not so hard. The nth derivative of this function, this is minus 1 to the n times n factorial divided by x to the n plus 1. To prove this is just induction, but I can show you why. Let's just do the first terms. F of x is 1 divided by x, to which I can write as x to the minus 1. So the derivative of this certainly is minus x to the minus 2, which is minus 1 divided by x to the 2. Okay, and the second derivative, if I just look at this, clearly is x to the minus 2x to the minus 3. And, let's just directly do another derivative. The next derivative would be minus 6 times x to the minus 4. And if you rewrite this as fractions, you recognize precisely the shape of this formula that I've written down here, right? Every time from the exponent goes down here and becomes a coefficient, this adds multiplication with another integer. This gives you this factorial term here. You already observe the alternating signs and, of course, the denominators. Okay, good. So if you want a rigorous proof, induction. So this is what we get here. So now I need to plug this in into this formula, and there's a slightly delicate point because I only need this for the even derivatives. So what I need to plug in is this expression here, but for 2n instead of n. So this gives me minus 1 to the 2n, then 2n factorial divided by z to the 2n plus 1. This is what I get. And note that this already looks promising because there is some funny cancellation happening. So first of all, -1 to some even number is always 1, so we can ignore this term. And then we have 2n factorial here and 2n factorial here, so these cancel. And you see we get now the Euler numbers divided by z to the something, and still a lot of powers of 2. Now, the next step I'll do might again appear a little bit unmotivated, but you'll see it will have the function to kill the 2 here, and it will be useful also in other ways. Namely, what I now do is pick a number, capital N, which is a multiple of 4. So when I say multiple of 4, I mean an integer multiple of 4. And we'll see why this is useful. And this being picked, I will just define z to be n½ So since this is a multiple of 4, n½ is an even integer. Okay, you'll soon see why this is useful. Okay, so I get 2 times the sum from lowercase n from 0 to infinity -1 to the n divided by n½ plus lowercase n plus 1½ equals the sum from 0 to infinity e to n, the Euler numbers, divided by 2 to the 2n. And now I have to plug in n divided by 2 for z, so this gives me n to the 2n plus 1, but also 2 to the 2n plus 1 in the numerator, by making the denominator in the denominator part of the numerator. So I get this formula. I'm already observing that there will be a cancellation of powers of 2 here, but let me do a simplification of the left-hand side first. Lowercase n starts from 0, but effectively, if you look at the terms which are in the denominator, this means that they start, if I ignore this, from capital N divided by 2. Yeah, and then I go to n equals 1, 2, 3, and here I have capital N½ plus 1, 2, 3, and so on. So I can just re-index this sum so that the sum starts with n divided by 2 instead of 0. So this corresponds to the transformation that I'm replacing n by n minus n½ The sum then starts from uppercase n divided by 2 goes to infinity, and then is -1 to the lowercase n minus n½ divided by lowercase n plus 1/2. Yeah, I've just applied this transformation here in the sum. So this is the same as this. Okay, and I can also simplify the right-hand side. So now I have this cancellation of the 2's. This gives me e to the 2n, and I kill this factor with this factor. 1, 2 remains. So I can write this as 2 times e to n divided by n to the 2n plus 1. Good. And now I really want to get this expression into the shape of the Leibniz sum. And all that I have to do for this is multiply the denominator with 2. Oh, wait, I can cancel these 2's. So if I multiply the denominator by 2, it means that I have to multiply the entire expression by 2 to compensate for it. This 2 here is not this 2, it's a 2 from changing the denominator. So n was a multiple of 4, so n divided by 2 is still even, so this won't affect the sign. So I get -1 to the lowercase n divided by, and now 2n plus 1. This is what I meant by multiplying the denominator by 2. And this equals this expression. And you know what? Now we're basically done. This is the remainder term for the evaluation of the Leibniz formula. Recall, pi divided by 4 was the same as the sum from 0 to infinity of -1 to the n divided by 2n plus 1. This was Leibniz formula. So what we evaluated with our little program was, of course, not this infinite sum, which is impossible to evaluate with a computer. But what we're evaluating was a sum only going up to some term. We were only evaluating a partial sum. We're only adding up to some certain lowercase n. And then we actually had a look at whether the digits are correct. So what we were measuring was the difference between this partial sum and pi to the 4th. So what the computer actually evaluated was n going from 0 to, say, capital N half minus 1 of this. Yeah, so this would be corresponding to what I plugged in for this value, which was called range in the program. I only evaluate up to a certain point. And then, okay, I multiplied this with 4, and I was comparing this to the correct value of pi. So this is the expression which we actually considered, and this is the expression where we can see what the wrong digits are. But now I can rewrite this using this formula I have up here, namely as follows. I plug in the infinite sum for this expression on the left, which is the sum from 0 to infinity of minus 1 to the n divided by 2n plus 1. And I still have to write this term here, which is minus 4 times the partial sum from 0 to capital N minus 1 of 1 and minus 1 to the n divided by 2n plus 1. And of course, since these are the same terms, they cancel, and what remains is only all the terms which occur after I've surpassed in this indexing the index capital N divided by half. So I get precisely the sum 4 times the sum starting from capital N divided by 2 going to infinity of this term. So let me repeat that. This is what our program in the computer computed. We only sum the Leibniz sum up to a certain term. Then we compare this to the actual value of pi, and this is this difference. We found a different way to express this, namely, this is this. But this is exactly the same expression as twice what I've studied here. So I can just multiply this equation here by 2, and then I get 4 times this equals 2 times this. So now we learn that this error that we see in the decimal expansion, the difference from the correct value of pi to what our partial evaluation is, there's a very different way to compute this, namely using this term involving these mysterious Euler numbers, of which we've so far not computed a single one. But so this is a different expression for this difference. And now I've achieved what I've been dreaming about. Namely, I wanted a formula where it's possible that there are powers of 10 occurring. The idea being that these powers of 10, if you divide by a power of 10, this moves the decimal places in the expansion. And I want to use this trick to move the decimal places apart so that I can understand what happens at individual decimal places. And this happens exactly when capital N is a power of 10. But this can be arranged, because so far the only assumption we had for capital N was that it's a multiple of 4. That's the only thing we've used. And 100 is the smallest power of 10 having this property. It's 4 times 25, so it's a multiple of 4, but it's also a power of 10. And any higher power of 10 also has this property. This means, for example, if you take for capital N powers of 10, then really the digit pattern you see are just these Euler numbers, and then shifted in the decimal expansion by this 2n plus 1 term. And this gives you exactly this error in this evaluation. So it's always cool in maths when you can do some predictions. So let me make cool predictions about the decimal places which are actually wrong. So remember we had evaluated these terms with our little program and then observed these interesting stretches of correct digits. Now, using these formulas, I can make predictions about which digits are wrong and how they are wrong. So I will explain to you how to compute these Euler numbers. I haven't said anything about this so far, but I'll explain to you later how this works. For the moment, let me just... I just looked them up. This is what's happening right now. So I have them here. So I evaluate this. So the first Euler number is 1. So I get 1 divided by... So this corresponds to lowercase n being 0. So this is 1 divided by n. So then the next one is minus 1. So minus 1 cubed plus, and then the next one is 5, n to the 5th. And the next one is minus 61. 61 n to the 7th, and so on. So actually the next one is 1385. And so on. Okay, the idea is now, with this formula, I can now make predictions about what the incorrect digits are. I will just pick n, so n needs to be a multiple of 4, and it should be a power of 10, so that I get an expression here which really decodes something in the decimal expansion, so I'll pick n to be 1 million. Okay, so this means I will evaluate this till 999. Okay, so this is what I'll have to evaluate here. But then I have really nice denominators, namely 10 to the 6th. So I get 2 times 10 to the minus 6, minus 2 times 10 to the minus 18th, and so forth. I predict that the 6th digit will be incorrect by 2, and then the 18th digit will be incorrect by 2, but in the opposite direction. And the good thing is we still have our computer program, so we can check whether that's actually correct. So let me Let's go back to the computer program. So here we are, and we had evaluated 500,000 terms. So this corresponds to this. Okay, so the prediction is that the 6th decimal digit is off by 2. Let's check that. So I'm here, and I see, so this is like 1, 2, 3, 4, 5, 6. And indeed, the 6th decimal digit is the first one, which is incorrect. Up here, I see there's a yellow box. So this one is the correct digit. It's a 2. So we see that actually the digit is off by 2. And this is exactly what the formula had predicted. And now at the 18th digit, it should again be off by 2. So let's check whether that's also true. So now, so this was the 6. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So okay, so here it should be off. So here you see 2 digits are incorrect. How does that come about? That's weird because our formula only predicted that the value would be off by 2, but this is actually exactly what's true. And luckily I can see the correct digits down here because they are yellow. So the correct digits would have been 3 and 8. And if you add 2 to 3 and 8, yeah, then sure enough, you get 40. So also this is correct. And we can also do the next. Here we see the digit is wrong. It's a 6. And since it's yellow here, I know that the correct digit is 7. So I expect there should be a correction by 1. So let's see whether this is also predicted by our formula. Yeah, indeed. So the next Euler number would have been 5, but remember we also have to multiply by 2, so this gives 10. This is at 10 to the minus 5 times 6, so this is at the 10 to the minus 30th, so this is at the 30th digit, but it places an error of 10, so the actual digit shift should be by 1 in the 29th digit. This is hopefully also what we get here. So I mean, so we definitely get a shift by precisely 1. This is exactly this 2 times 5. And this should be the 29th digit. Should I count it or should I not? I don't know. Let's just do it. Why not? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Yeah, okay. So you see, so this formula works. And yeah, well, now we've already learned a little bit about how to use this formula. I mean, it's amazing. You have perfect control over the decimal expansion. It tells you precisely at what places the digits are wrong. But you see already here now a different effect. Something that wasn't maybe clear so far is that the Euler numbers, they actually grow very, very quickly. They started slow, but then they increase drastically. And so already here we had a shift because 2 times 5 was 10. So really the digit which is affected was not the 30th, but the 29th. And this effect only gets stronger as you go further terms down. Now the numerators also span over several digits. So the denominators, they only have the effect that they shift the seed point where some error gets introduced in the decimal expansion, but then these errors themselves, they will have several digits, so they affect already a stretch of digits. But you also see that once n is very large, pick an extremely high power of 10, then these increasing powers in the denominators, they really space out these summons. So there will be large gaps between the individual summons. And since this controls the entire error in the formula, it means that anything in between these large spaces, all these digits must be correct. And this is always only an effect early on in the decimal expansion, because eventually, because the Euler numbers increase so drastically, they also become very long. So even though there might be a big spacing between the ends, the Euler number might be very big, so it might completely fill up the space between two such summons here. We've just used this function now for f being 1 over x, but you can use this strategy in a much more general setting. Another cool application, which is very close nearby, is if you just replace 1 divided by x by a power. Let r be some integer, and let's assume maybe at least 1. The case r equals 1 would be a special case of the consideration we've done so far. So the left-hand side now becomes 2 times the sum from 0 to infinity of the alternating sum minus 1 to the n, now divided by z plus n plus 1/2 rth power. And now for the right-hand side, I have to compute the derivative, the nth derivative of x. This will be minus 1 to the nth times r plus 1 and so on till r plus n minus 1 divided by x to the n plus r. So this is the general form of this derivative, and you get this exactly the same way as you proved it in the previous case. The induction is very similar because basically the 1 divided by x to the r was up to a factorial and a sign, already a step in the previous ladder of derivatives. Yeah, so this is why this is such a similar formula. Okay, and so on the right hand side we then get the sum from 0 to infinity. This is the Boole formula. So I get the even indexed Euler number, then 1 to the 2 to the 2n factorial, and then the nth derivative. And again, be very careful. I can use this formula now, but I have to remember that I have to plug in 2n for n here. So I get minus 1 to the 2n, then r times r plus 1 till r plus 2n minus 1 divided by x to the 2n plus r. There you go. This is our new formula. I will just pretty much modify this in the same way. So because r can be 1, this is really just a generalization of the previous consideration. Pick n, capital N, a multiple of 4. I choose z to be n half. So then I get 2 times the sum from lowercase n 0 to infinity minus 1 to the n. 1 divided by capital N divided by 2 plus lowercase n plus 1 half to the r. This is the same as the sum from 0 to infinity. And now let me simplify this term on the right hand side a little bit. So this is e to n, and as before, as in the case r equals 1, I have this term here. This disappears because this is always 1, and so e to n, then divided by 2 to the 2n factorial, then divided by z to the 2n plus r. This now comes from plugging in capital N divided by 2. The power of 2, I get this 2, so this is in the numerator, 2 to the 2n plus r. And then this term here, so this is r plus r till r plus 1, and so on, r to plus 2n minus 1. So very complicated expression. As before, I do the shift, yeah, so I replace n by n minus capital N half, so I get the sum for starting from capital N half minus 1 to the n, then again shifted minus capital N divided by 2, but because capital N was a multiple of 4, this is an even number, so this doesn't change the sign, divided by n plus 1 half to the r. And on the right hand side, let's have a look. So first of all, this 2n, 2 to the 2n goes away against this. E to n, then 2 to the r divided by 2n factorial. And now I can rewrite this term here also as a factorial, because I can just write r plus 2n minus 1 factorial. This then is the product from all the numbers from 1 till that. But I don't have this full product here. I only have a product here which begins at r. So I can write this as r plus 2n minus 1 factorial, and then just divide this by all the factors which are missing. So this is divide this by r minus 1 factorial. It gives me the same expression as I have up here. This thing here is exactly the same thing as this. Good, what am I missing? I still have divided by z to the 2n plus r. Good, now let's simplify this a bit further. Again, I want to have the odd numbers here and not just integers plus a half integer. So I'll have to multiply this expression down here by 2. This is already what I did in the r equals 1 case. But now I have r factors. So I need to have a factor of 2 for each of these individual factors. So I really have to multiply the denominator by 2 to the r. So to compensate for that, I'll also have to multiply the prefactor by this. So this is the same as 2 to the r plus 1. Yeah, I'm adding 2 to the r as a factor of the sum from capital N half to infinity. And now I can add a 2 inside each factor. So I get 2n plus 1 equals r. And on the right hand side, I get a sum. Oh, okay. So one thing which is really cute is that I also got 2 to the r. Yeah? So I'll be able to cancel this soon from the left and the right side. So I get also the even indexed Euler number. I observe that I can write this in a different fashion, because this is the same as a binomial factor r2n minus 1 over r minus 1. Maybe I should unravel that. If I unravel this binomial factor, that's the same as r plus 2n minus 1 factorial divided by r minus minus 1 factorial, and then remember the remaining factor is the upper thing minus the lower thing. So r plus 2n minus 1 minus r plus 1 factorial. R cancelling against a minus r, and then a minus 1 cancelling against a plus 1, so I only have 2n remains. So this 2n is the same as this 2n, this r, remember there's a factorial, then I have r minus 1 factorial, this is the same as this, and then I have this numerator, which is this. So I've just rewritten all of these 3 factorial terms in terms of a binomial coefficient, and then I still have divided by z to the 2n plus r, and that's it. I think I have implemented all the factors. Now in the last step, I can cancel the funny factors of 2r on the left and the right side. So this is the same as 2 times the sum from capital N half till infinity of minus n to the 2n plus 1 to the r is the same as the sum from 0 to infinity of, how to write it? Well, r plus 2n minus 1 over r minus 1 binomial factor e2n divided by, why do I still have z? So sorry, at some point so I forgot to plug in the n, so this was, I apologize. Remember n was z half, and I even implemented the corresponding factor up here. I apologize. So this is not a z, this is an n. This is an n. So divided by n to the 2n plus r. Cool. Now, it's very good that this is a binomial coefficient. If this was, as it might have seemed initially, if we had a lot of complicated rational factors up here, at first sight it looked as if we had some of these factorial factors, and these would mess up everything, because the whole strategy was to let capital N be a power of 10, so that these summands would space out the contributions in the decimal expansion. But if you then additionally divide by some crazy rational numbers, this messes this up completely. Imagine you divide by 3. The digit pattern is 0.33333, so this completely would mess up the whole story. We are very lucky in a way, or I don't know, maths is very lucky, that we could simplify this to a binomial coefficient, because that now means that this term is an integer. It won't have the destructive effect of actually dividing by some other number here. Yeah, okay, and now, we can run the same pattern. So first of all, we observe that if I plug in 1 for r, I get precisely the formula which I had before. This is a generalization of the previous formula. Now let's use it. So let's make a prediction now for something which we haven't computed. So now we really want to see how strong our technique is. So I'll pick r equals to 3. And so remember, so the formula which we just had, I'll just write it down again for r equals 3. So this was the sum lowercase n starting from capital N halved minus 1 to the n divided by 2n plus 1. Now this is cubed. And this is the same as the sum from 0 to infinity of 3 plus 2n minus 1 over 3 minus 1, the binomial coefficient. And then the Euler number is e to n divided by n to the 2n, and now r was 3. So this is the formula which we've just developed in the concrete instance r equals to 3. Now, first of all, this would be the sum. Remember, this is just the error term. When we do partial summation up till the n halved minus 1 term, then this is the error term which we get. To compare this actually to the limit, we first need to know what the limit is. So this would be 2 times just the alternating sum of the odd powers of the cubes of the odd integers. Now I happen to know what this thing is. So this is 2 times. So this expression here, this is pi cubed divided by 32. Let us just accept this for the moment. I'll explain to you later how one can possibly know what the limits of such series are, but for the moment let's just accept this. So this is pi cubed divided by 16. So what I would now expect is the following, using our strategy. If I use this series to compute pi cubed divided by 16, then I expect that when I only evaluate the sum partially, which is the only thing I can do in a computer, that the incorrect digits of the partial sums are completely predicted by this term. So let's evaluate this. This thing here is the sum from 0 to infinity, 2 plus 2n over 2 and e2n over n to the 2n plus 3. So let's maybe just check out what should be the first incorrect digit. Again, for n, capital N, 1 million. So as before, this is divisible by 4 and it's a power of 10. So I have this effect of the decimal expansion getting spaced out. So the first summand is for n equals 0. Then I get 2 over 2 times e0 over n cubed, which, so the 2 over 2 is 1. The first Euler number is 1. And n was 10 to the 6. So I expect the first error to be 10 to the 6th to the 3rd. So the digit should be off by 1, and the digit which is off should be at the 18th place. This is my prediction. And I think we should check that. So what I'll do is I'll just use exactly the same program as I've used before. So here it is. And we'll just modify it. So recall, how did that program work? We're starting with a value 0. Then I have a for loop. It's also indexed by lowercase n. It goes from 1 till whatever is the range. And then here, because this was still the original Leibniz formula, I had this alternating sum over the odd integers. Okay, so now this changes a bit because we're not taking the inverses of the odd integers, we're taking the cubes. So this has to be cubed. And also I'm not multiplying by 4, I'm multiplying this by just 2. So this should be a 2. Okay, and then also in the end, I shouldn't be comparing the value to pi, because this time I'm not expecting the value to be pi, but the value is pi cubed divided by 16. Let's have a look. What we definitely can see is that the effect is happening as before, because also here you see these long stretches of correct digits, which you would usually never expect. These scattered yellow dots, as I explained in the beginning, these are just digits which are completely accidentally correct. There's a 10% chance that a digit is accidentally correct. But these long stretches here, this is a pattern. This is not noise. And now I've forgotten what my prediction was. Wait a sec. So the prediction was that the 18th digit is off by 1 after evaluating 500,000 terms. So this better here be at the 18th digit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you see what we actually get here is 59, and the correct value is 60. So indeed, at the 18th place, there is an error of precisely 1. So you see it works. This technique works. And, you know, the next error here, it could also be predicted by this formula. We only would have to evaluate the next term here. So the Euler numbers perfectly predict all these incorrect digits. And it's really amazing, because it means that in a way, if you really wanted to compute the decimal expansion and you are fine with making a mistake occasionally in some digits, then it's much smarter to evaluate 500,000 terms than 600,000 terms, because you see 600,000 terms, it has these two digits right, but you know, the 500,000 terms evaluation has many more digits right. So this is really a cool effect. Yeah. The next thing I think I should tell you is how to actually compute these Euler numbers, because so far I've just been telling you what these values were, 1, -1, 5. But of course there are good strategies to compute them, and this I guess I should tell you next. There is an interesting aspect in the definition of the Euler numbers which we haven't explored at all, and we'll do this now. And that's the following. Recall that the Euler numbers were defined as the coefficients in the expansion of this function. We had already observed that all the odd indexed coefficients are 0, so it's okay if I only list the even indexed ones. So this was the power series which forms the definition for the Euler numbers. And I had already told you that this is the same as the hyperbolic cosine of x. We haven't used this link to geometry at all, so let's do this now. Recall Euler's formula. So e to the ix is the same as the cosine of x plus I times the sine of x. And this really motivates to plug in ix for x, because you can solve this equation for the cosine and you get this standard formula. The cosine of x is the same as e to the ix plus e to the minus ix divided by 2. And this looks very similar to this expression. So let's plug in I for x here, and then I get 2 divided by e to the ix plus e to the minus ix, which as we see is exactly the same as the inverse of the cosine. So this is the same as 1 divided by the cosine of x. This is exactly this effect that the hyperbolic cosine is just the cosine rotated by 19 degrees in the complex plane. Okay, and now I plug in ix in the right-hand side for this formula. So I get the sum from 0 to infinity of e to n times I to the 2n times x to the 2n divided by 2n factorial. But I is the square root of minus 1, so I squared is minus 1. So I obtain the following very nice formula. 1 divided by the cosine of x is the same as the sum from 0 to infinity of e to n times minus 1 to the n x to n divided by 2n factorial. And this cute formula, this can be used for many things, but in particular it can be used to actually compute the Euler numbers. The idea here is that we simply multiply this identity with the cosine now, so we get something times the cosine equals 1, and from this we can obtain some curious identities between these Euler numbers. Let's do that. So I multiply this with the cosine. And I directly will use that we know the power series expansion of the cosine around the origin. That is the sum from, I will index it by m from 0 to infinity of minus 1 to the m times x to the 2m divided by 2m factorial. That's just the power series expansion of the cosine of x. This is the cosine of x. And now I multiply this with this thing. So this is the sum from 0 to infinity of minus 1 to the n x e to n x to the 2n divided by 2n factorial. This is now 1. This is exactly what I get out of the previous equation by multiplying by the cosine. Okay, and now I'll just unravel what this product of series is, which might look complicated, but it's not too bad really. I will collect the terms which have the same exponent of x. I will only need even indices. I will call this variable v. So v goes from 0 to infinity, and now I'll sum over all the terms nm, where the sum of n plus m is v. Here I collect all the terms where the exponent, once I multiply the x's, is v. The terms are minus 1 to the m times minus 1 to the n, so now I have these two. Then e to n, and then divided by 2m factorial times 2n factorial. And then all this goes into a big bracket, and then it's times x to the 2 to the n plus m, but n plus m is v, so this is x to the 2v, and this is 1. As soon as v is at least 1, I know that this sum must be 0, because the expansion coefficients of a power series are uniquely determined. I have a power series on the left-hand side, and I also have one on the right-hand side, except for that it only has the constant term. So I know that all the other coefficients for the higher terms, they must vanish. This is the whole trick in this method to determine the Euler numbers. For all v at least 1, I obtain that this sum, and now I'll write down this sum in the bracket here, but I'll already re-index it. So instead of writing this in two indices whose sum is v, I'll remove the variable m. So I'll just index this from n going from 0 till v. N can at most be v because m has to be non-negative, so from 0 to v. Everywhere I have to replace m by v minus n. So minus 1 to the n minus v times minus 1 to the n, then e to n, and now divided by 2 times v minus 2n factorial times 2n factorial. Yes, and this is 0. This looks a little bit like a binomial coefficient, but something in the numerator is missing. So let me just multiply all of this with 2v, with the factorial of 2v. I can do that because the sum is 0. So if I multiply it with something, it still stays 0. So I get the sum from 0 to v. Then here, if I multiply these two terms, I have n occurs twice, so this doesn't affect the sign at all. And then I have a minus v, but this doesn't depend on n, so the entire term gets multiplied with a sign. I can just multiply the whole equation with a sign to make this positive. So I can ignore these terms. By the way, this is wrong. This should be v minus n. It doesn't matter. It's still the same. So the two n's cancel out. Then I have e to n. Then I multiply the whole thing with 2v factorial, and then I divide by 2v minus 2n factorial 2n. And now this should be 0 times 2v factorial, but that's 0 again. We recognize that this is the binomial coefficient 2v over 2n, because if I unravel what that is, it's 2v factorial divided by 2n factorial times 2v minus 2n factorial. That's exactly what's written there. This simplifies to the sum from 0 to v of 2v over 2n of e to n being 0. And this is the key identity to determine the Euler numbers. So remember, this is valid for all v at least 1. So how do I determine E0, E0? I could use the same strategy as before. I could evaluate the term here, but you can actually see this much more easily if you just start from the power series in the beginning. Let's just plug in 0 here. Then on the left-hand side, the exponential function at 0 is 1, so you get 2 divided by 2, so the left-hand side is 1. And if I plug in 0 here, then all the terms get killed except for the constant one, which is E0. So I get E0 times 1 equals 1. So very easily, we can already see that E0 is 1. I also know that we had shown this long ago, that for all n odd, En is 0. So I'm only interested in the even ones. So it's very convenient that the even ones occur in this formula. Let me show you how to use it. Let's start with v equals to 1. Then I get a sum with two terms. N will be 0 and 1. And for 0, I get, so v is 1. So I get 2 over 0 times E0 plus 2 over 1 times 2 over 2 times E2, and this is 0. Okay, and since I already know what E0 is, it's this, so this is 1, this is 1, this is 1, so I deduce that E2 has to be minus 1. So see, I've already computed the next Euler number. Let's do one more. Now I use the formula for v equals to 2, so I get 3 summons, and these summons will be 4 over 0 times E0 plus 4 over 2 times E2 plus 4 over 4 times E4. Now let's compute this. So 4 over 0 is 1 and E0 is 1. So this is a 1 plus, now this is more complicated. So this is 4 factorial over 2 divided by 2 factorial times 2 factorial times E2. I know what that E2 is minus 1. Plus 4 over 4 is 1 and E4 I don't know. This is what we'll compute now. So this is 1 plus, okay, then, okay, 1 times 2 times 3 times 4 divided by 1 times 2 times 1 times 2. These two cancel. 3 times 4 is 12, divided by 2 is 6. So this will be minus 6. This is minus 6 plus E4 is 0. So I see E4 is 5. And now with the same strategy, you can compute all the Euler numbers. A formula like this might not be very easy to remember. So let me just show you a cute little trick how to remember this formula. Write e plus 1 to the 2v plus e minus 1 to the 2v equals 0. Now you might be wondering, what is e? It's not an Euler number. At the moment, it's something new, and it's nothing. It's just a variable. We just call it e for suggestive reasons, and we just study this equation. So far, no relation to the Euler numbers. But let me quickly expand what this equation is. I can just use the binomial theorem, write this as a sum from 0 to 2v, binomial coefficient 2v over n of e to the n, and then you don't see the second summand because it's 1. It's 1 to the 2v minus n, but since it's powers of 1, you don't see anything. And here it's basically the same, just with a different sign. So you get a sum n from 0 till 2v of 2v over n, again e to the n, but this time minus 1 to the 2v minus n. And this is 0. Cute. But now you observe something. These two terms, they look very similar. And indeed, except for the minus 1 here, they are similar, right? This is exactly, I mean, that's the same. This is exactly the same as this. So what really happens here is that when n is odd, you get minus 1 here. The 2v, that's an even thing. It doesn't even affect the sign at all. We could strike this out. If n is odd, you get the same thing as here, but with a minus sign. So these two terms just cancel out. But if n is even, you get exactly the same. So in the sum, you just get this term twice. So there's a nice way to rewrite this. Namely, we consider the same sum, but now we only consider the even terms, just because the odd terms here cancel out. And the even terms, they appear twice. So this is 2 times 2v over n e to the n, and this equals 0. Now, of course, since this equals 0, I can just get rid of the 2. This will also be 0. And now, instead of just going through all the numbers from 0 to 2v and then filter out the even ones, I can also just reindex this only running over the even numbers. So this gives me the sum from 0 to v now over 2v over 2n e 2n equals 0. This gives me a really nice little cute equation. The trick for all this is, of course, to compare this to this formula that we had a look at earlier. Here we had the proper formula to compute the Euler numbers. And here we have this formula which came out of this other expression with this variable e. So if I now take the exponent to n and I would just decide to drop it and write it down here, I'd get exactly the same formula as here. All you have to remember is this formula up here, which is maybe easier to remember because it's very symmetrical. You expand it and then you just let all the exponents drop down and become an index, and you get the correct formula for the Euler numbers.
It's perhaps a good moment to wrap it up now, so let me close here. A few more remarks. This is not just a story about decimal expansions. You could also do this to other bases. Remember, we had this parameter capital N. This would just had to be a multiple of 4. But for example, capital N could be some power of 16. You could work to base 16 or many other bases. So this is not just a phenomenon which happens for decimal expansions. It happens with respect to any basis which is a multiple of 4. Another thing which is perhaps more important is I was glossing over the convergence issues with a Boole summation. These issues are actually substantial. So I will not explain this here, and I'll just refer you to the paper, which is linked. But really, this Boole summation, this statement is literally true for polynomials. But if you, in the setting that we work with in this video, you would actually carefully need to control the error terms. The error terms are substantial. Yeah, this is not really convergence. Yeah, that's it. So I hope that was fun somehow. And yeah, play with it, because you can apply this Boole summation trick not just to this particular series, you can apply it to many other series and get similar phenomena. So this is also very interesting.